our final talk of the day, but certainly not least, Dougal.
So, looking good.
Looking good, sounding good. Take it away.
Awesome, thanks. Yeah, so sorry I couldn't be there in person, but I definitely really appreciate the opportunity to kind of talk about this work and close down what's been a really awesome kind of selection of talks today. So I'm going to be talking about a project that's ongoing. We did a about a month-long campaign last year, and we're going out again this summer. And depending on funding, could potentially continue for a few years after this. And that's characterizing what we believe to be like soft-bedded glacier sliding in Taku Glacier's ablation zone, kind of using integrated borehole and geophysical experiments. In the initial title of this talk, I also included numerical experiments, and a larger goal of this project is to kind of use these observations to model Taku and model its hydrology. But at this stage, I'm just going to kind of focus on the empirical observations. And I'll note that this project has a lot of people involved. On this screen, I have listed, a selection of co-authors from, Wisconsin or University of Alaska Southeast, like Lynn and Jason, Arlick from Hokkaido. And there's other people that are involved, but the people on the screen have kind of at this stage like directly contributed or to both like data collection, experimental design, and kind of leading the kind of like the direction of what we've been doing in the field so far. And I'll note that so my interest in Taku's Terminus actually started in about 12 years ago in 2014. I was a student on JERP. And at that time, we would do these, we had a student project. And so they flew me and a couple students out, and we met Jason at the terminus of Taku and camped out there for about a week doing ice penetrating radar, checking on the GPS stations. It was just like an all around, pretty transformative, awesome experience. So when I was a postdoc with Luke in about 2023, Seth sent Luke an email kind of talking about the new drill and asking if there was any ideas for, kind of instrumentation at the ice bed interface, that might be a potential, kind of target to do. And so me and Luke started scheming, thinking about, opportunities to start, like study soft bed glacial slip. It's kind of a big component of my PhD and postdoc. And Taku's Terminus was just kind of like a natural setting to explore these. This got a lot more interesting when I was kind of met up with like Jason and Lynn at AGU in 2023, and they were showing me plots from this paper that Lynn was describing that has recently come out or recently been accepted, where you have this asynchronous seasonality at Taku's Terminus, where this like eastern lobe kind of does this, maybe kind of canonical spring to summer, acceleration deceleration cycle, where the western part of the lobe, Piedmont lobe, starts accelerating, in early summer and kind of continues through this melt season, tracking with melt input to the bed. And I found that to be really fascinating. I think that this is like, as Luke says, this is a world-class glacier. There's very few settings like this in the world that, kind of showed these contrasting seasonal dynamics. And I think that it like, given Taku's size, the fact that it's like a large glacier, higher latitude, with surface melt being fed to the bed, is like a pretty interesting analog for some of this, kind of contrasting seasonality that's been shown to occur on Greenland's outlet glaciers. This is a plot from Twyla Moon's paper, kind of showing that, even with like really, kind of similar settings, you get like neighboring glaciers kind of with this kind of contrasting seasonality that probably relates to hydrologic conditions or, geometry at the bed. So this kind of like motivated us to kind of like shift the kind of perspective of this like this field work or this project that we were starting to try to spin up and think about like first of all like how do these bed conditions that underlie Taku Glacier, what are they and how do they drive this contrasting seasonal behavior that Lynn and Jason have discovered? And then second, kind of going back to what our initial like thought was, is like, can we use like this setting, like Taku's kind of like unique dynamics as a natural laboratory to kind of study soft bed slip and sliding, within the subglacial hydrologic system, in a way that's, kind of like very high resolution, a lot more detail that is, kind of maybe been able to have been captured for a soft bed, and then use these observations to think more broadly about, soft bed sliding in larger systems like the Greenland ice sheet. So, kind of the first question, right? What's at the bed? Lynn was talking about this. My initial kind of impression of Taku, based on the available literature at the time, was that, kind of at this terminus, it's underlain by kind of a silty, clayey till. So this is a kind of a photo of the kind of basically where the ice meets these terminal moraines, at the edge of the ablation zone. And then what's in the literature, right? So this is from Jenna's paper, kind of showing sediment redistribution, beneath Taku's terminus. And in this paper, they show these five green dots, which represent boreholes that were drilled. And then, in another paper, they talk about using, gravity core to retrieve some sediment. So right at the center of this, this terminus, this ablation zone, they've pulled out till, and they describe it as a silty clay or a sandy clay. So a very fine-grained clay till with a 26% water content. And note that this is, kind of in the zone where it is doing that kind of spring to summer speed up. And then over on this right side is where you have kind of this more perhaps distributed system. So also, other lines of evidence through, active seismic, doing amplitude versus angle analysis and radar. Kind of there's this idea, at least going up to this like center stretch of the glacier, that there's, a pretty significant and thick layer of till that kind of continues for a few kilometers up glacier before potentially pinching out upstream. And then as Lynn was showing, right? So this is this historical image from 1948 with the kind of this surface or the day of the year reaching peak surface velocity kind of overlaid over the top of it, where you see that right on this kind of this western lobe where the glacier overrode it, you have this Norris Glacier outwash plain. In the center, where it's kind of peaking in velocity earlier in the year, they've pulled out a fine-grained till, and then over on this what eastern side, which might have been inferred to be till previously, there's been it's kind of an open question. Perhaps there's sediments, perhaps there's sediments with different properties, perhaps it's eroded down to bedrock, and that's kind of driving this different like dynamic regime. Currently, we don't really know. So at the moment, this question of what's at the bed is open. So potentially, it could fall into this category of a mixed bed, mixed bed rheologies with some sort of hard to soft or rigid bedrock to kind of soft granular sediments transitioning somewhere along the glacier. It potentially could all be sediment still. So you could have reworked sediments with till contrasting with reworked outwash sediments, perhaps different hydrologic properties or different states of compaction. I think either one of these are really interesting conditions and really kind of make this a really unique and interesting glacier to study because it's kind of like this emerging realization of the way that we think about glacier beds, hard versus soft. In nature is not really always the case, and often not the case. So this is a callback to Luke's mosaic that I screenshotted. I thought it was really cool. But this idea that like for a lot of glacier beds, the bed is a patchwork or a mosaic of these different kind of elements, and how the ice interacts with these elements, like in aggregate, determines the large scale dynamics of glacier flow. And kind of as an aside, like this basal hydrology at Taku is particularly puzzling to me. What haven't been out there a lot, but like walking around at the terminus, you see that Taku's kind of inferred or inefficient drainage area, that western lobe, overrides an old outwash plain. If you walk around, the outwash in front of the terminus, at least in the areas where I was at, you see a lot of sandy sediments, kind of mixed in with like coarse cobbles, definitely with patchworks of like finer grain or silty sediments, which just that kind of that coarse sediment or higher hydrologic conductivity, you might think it would support a more efficient drainage. And then in contrast, right, you have this like subglacial, like the only direct subglacial access that's like basically been punched through in the central area of the terminus, recovers a really clay-rich till with lower conductivity, which might support, you think like an efficient drainage, but that supports pretty like, apparent channels, that are draining at the terminus. And so kind of in my mind, it's a really interesting question of why does Taku kind of appear to show maybe the opposite of what you might expect just based on sediment properties alone. It's possible that the Norris outwash plain is, a completely different granulometry than what's, we're seeing in front of Taku. And ultimately, what this is saying to me is that it really motivates, subglacial axis, like Luke was talking about, and retrieving some of the subglacial till in these different areas that are exhibiting these contrasting dynamics. And so for this first kind of motivating question, this objective is, we're trying to constrain bed properties, and this is building off of approaches that the university, teams at the University of Alaska Fairbanks, like Martin Trufer's group, and then Jason at UAS have been, kind of doing for a while now. So using active seismic surveys with amplitude versus angle, so looking at like changes in the reflection coefficient and how that kind of relates to theoretical like relationships for different bread properties. Second, like which we talked about a bit, and we're planning on doing this year is direct borehole access. So you can use a camera to physically observe what's happening at that ice bed interface, and then as Jacob was just mentioning, which is awesome to hear, potentially grabbing or coring some of the sediment for future lab experiments. So characterizing it through geotechnical tests to really kind of get at like how these bed properties could be affecting these like larger macro scale dynamics. We're also trying a passive seismic technique called HVSR, which can potentially give some information if there's significant contrast and impedance between the ice and whatever's underlying it. We'll see how that works out. For the second kind of like, motivating question is like, we want to know if we can use Taku Glacier as a natural lab to study these soft or potentially mixed bed hydrology and slip. And I'm not going to go too in the weeds with this, but kind of the idea, right, is that assuming this is all till, which it might not be, the way that water moves around and is stored, and the architecture of that subglacial drainage, is a function of the effective pressure, the ice overburden minus the subglacial water pressure and the discharge, right? And where you're at, and then the surface slope of the ice as well. And so, like where you're at in that regime can lead to, very contrasting styles of subglacial drainage, like unstable sheet flow or kind of distributed, kind of porous flow or just inefficient flow in general. But you can move into a regime where you get really efficient flow through kind of R channels that are incised up in the ice. And kind of coupled to that, is this idea that basal motion is like basically, intrinsically linked to how this water is distributed in the subglacial system. And, as you do things like, increase that water pressure, you can change like the slip regime from, something where you have basically a lodged till with ice having to flow around like these roughness elements or lodged class where you start increasing the water pressure and you start decoupling the ice from the bed, weakening the sediment itself, kind of allowing slip at the interface and some component of deformation with it until, or if you keep increasing that water pressure, you can just completely decouple that ice from, that sediment bed locally. And all of these are kind of, these different slip regimes could be happening, kind of at the same time, right, across a glacier's bed, depending on how they are located within the context of these different glacier drainage features, right? So, a distributed system where kind of ice is trapped in canals or ponding, you might have high water pressure, low effective stress, leading to certain styles of slip where you have, R channels or efficient conduits, you maybe get higher, effective pressure and a different kind of slip regime. So if you have, something, a means or a geophysical tool where you can kind of monitor these different processes, then you might be able to use something like Taku as a really interesting kind of natural lab to explore that. And so passive seismics are very useful for this. And so there's been a lot of, really good work in recent years with passive seismic processing techniques on hard beds that have shown that you can, in pretty high resolution, if you have a sufficient array geometry, you can map turbulent subglacial water flow in time and space, with a pretty high precision of, location. And similarly, there's a recent study that we conducted on Saskatchewan Glacier in Canada, where kind of showing that basal frictional like stick slip events kind of concentrated in the vicinity of a subglacial, like an R channel, basically. And how the dynamics of how these things were popping off is directly related to kind of the timing and volume of water that was being input to that bed. So this hasn't been done on a soft bed, at least that I'm aware. And so this idea of using Taku as this natural lab, kind of our idea is this, right? So you have these two kind of contrasting lobes. This western lobe, that starts speeding up, kind of late spring that we believe is kind of a distributed or kind of exhibits characteristics of a distributed or an inefficient system. Then you have this eastern lobe that's kind of exhibiting characteristics that are consistent with a channelized system. And so what we're I are proposed to do, or what we went out and did, is to kind of put dense seismic arrays in each one of these lobes that can measure, or record like turbulent subglacial water flow to help us like kind of delineate like channelized systems from distributed systems across this terminus. These seismometers are also able to kind of measure basal stick slip, right, or the lack of basal stick slip. And then kind of those two measurements together, those observations together, kind of allow us to contextualize these styles of basal slip like in the context of a subglacial drainage system or subglacial drainage network. And then on top of that is to use these like this direct borehole access and these seismic observations to kind of contextualize where we could place some of these borehole instruments like this cone penetrometer that Luke talked about, or a plow meter, or water pressure sensors to kind of get like high resolution constraints on things like bed strength, water pressure, like slip at the bed, that can be used to inform the larger geophysical observations that we're getting from the seismic network. So that's kind of like the overarching goals. And so last year we went out for about a year and did a number of kind of geophysical tests. So just kind of like a summary, we deployed 88 smart solo 3-component nodes and two 44 node dense arrays, so about 100-meter spacing, kind of co-located with these seismic networks were two continuous Trimble GNSS stations that Jason Amundsen and Lynn had put out much earlier in the season. And then on top of that, we were taking repeat GNS surveys using like an IMLID RTK rover of each node, basically every time we service them with an ablation measurement, like every 3 to 4 days. To kind of contextualize these seismic observations, we're getting a number of environmental measurements, so surface temperature at different elevations up the glacier, precipitation and temperature at camp with a weather station. We had basically an acoustic sensor that measured kind of noise at the proglacial outlet channel. That was something that Arlik Chang measured from Hokkaido. And then we also did a number of active seismic surveys, both in the east and the west, using AVA with 1-component geophone string, and then just shooting normal incidents directly into the 3-component nodes that we placed out. So this was a pretty big effort. In kind of jerk fashion, I labeled them blocks. So we had basically people coming in every week relieving kind of with helicopter support from different universities. So block one was three PhD students from Luke's group at the University of Wisconsin. Block two included, Lynn, Kaya, Arlik from Hokkaido, students from University of Alaska Fairbanks. And then block 3 and 4, we had, students from, WashU and the University of Chicago as well, with Luke out there. So yeah, it was a long effort. Basically me and one other student were out there for the full month, and then people were coming in at, week or 2-week intervals. And so this is a plot from Lynn's paper kind of showing this surface velocity time series for these two GNS stations that were kind of relatively co-located each one of these arrays. And the shaded area is basically how long at least some of the seismometers were out. So, they take a bit to get in place, but we had them out from, about up to a month. And yeah, what you see, like as Lynn was describing, is that, at this kind of portion, you have this kind of decreasing trend in velocity along the eastern array, with this velocity that starts ramping up in the Western array with much stronger kind of amplitude oscillations, corresponding to the water input at the bed. And so this is kind of showing the two arrays as we ended up putting them out. Initially, we had planned to put this eastern array, this bluer one, kind of down further towards the terminus, but that was absolutely not a tractable thing to do. When you get down there, it's extremely cracked up and dangerous. And so this western array, and then these red dots represent temperature sensors that we brought, or Kaya brought out, that we installed for about a week in order to get a lapse rate and constrain a positive degree day melt model for our observations. Yeah, so this is kind of a quick summary. We had about 88 nodes deployed across these two arrays, less than 100 meters spacing. Deployment period was around, June 2nd to June 29th. High melt rates in this area, I forget the exact value. Maybe it's like 9+ meters. I think Lynn said it. It's a lot of melt that's occurring, at basically sea level with this glacier, and that really kind of complicates like how you're able to kind of service and deploy these instruments, which I'll take a little bit of time to talk about. And yeah, at each node we would co-locate it with an ablation stake and then survey it in every time we went back to it to survey it. This is just giving kind of a sense of what these, where we're putting them. On the west side is also quite cracked up, but able to navigate. And on the eastern side, it was definitely more, manageable, flatter, but you'd get more, moulins and ponds and surface runoff on the east side of the array. So, putting passive seismic, installing a passive seismic network in a high melt ablation zone is kind of a tricky process. And so this, next few slides, I'll just kind of give you a sense of like how we did this. It's a very labor intensive effort. I think my Apple Watch was telling me that, we were averaging 15 miles a day walking between up to these arrays to service them and then walking in between them and kind of setting them all in. And so what we are using are these smart solo nodes, right? And they come with these kind of like this little array of spikes at the base. And ultimately what we want is we want these things to be coupled firmly into the ice so that vibrations in the ice are able to transmit cleanly into the instrument. And we want these instruments to continue communicating with GPS satellites. And we also want them to, yeah, basically stay in place for as long as possible. And kind of the trade-off that we settled on, and the method that we chose to do. This was initially developed by a person in my PhD cohort, Nate Stevens, for a project we did out in Canada. The idea is that we built this kind of custom, what we call a melt-in tool, which is essentially a copper replica of the shape of the base of this node. And so at each site, basically what we do is you go there and you take a 6-inch auger and you drill about like a 0.4 meter hole. You heat the node, or you heat this melting tool that's shaped like the node over an MSR camp stove until it gets hot enough that you can then just kind of like, with the orientation correct, just push that thing down into this little borehole. And you'll melt in the shape of the spikes, and then you can just slot that node in into the hole, pack it back with ice chips, and then you can get it, for about like 3 or 4 days before it is, kind of needing to be reserviced. And this worked out pretty well, although it is a bit time intensive. So this is just showing, kind of another stage of the process, setting it in. We've drilled the hole, kind of melted the spikes in, and then Jaden is now kind of orienting to the azimuths to kind of set the azimuth on the node pointing north. This is kind of showing at the very end, once it's kind of in place, it's buried, and we kind of keep this bamboo pole or the stake in the same position that we then kind of survey in at each different time we went out to it. So we kind of get like a strain field that's kind of evolving on 3 or 4 day intervals. There's a lot of melt, like I said. So this kind of if you wait too long, you basically lose a day. So On the left, there's a little bit of tilting, a little bit of rotation that can occur at when we service these things. We're taking the strike and dip and the azimuth as we find them, and we can then like kind of correct the seismic data in post-processing. If we wait too long or if it just gets too warm, the node falls out, and you have to go in the data and kind of clip out those periods where it's just not gonna do anything for you. One thing that's pretty cool, this was a new one for me. We were sharing the camp area with a pack of wolves. So this is a photo I took of my footprint right outside of camp, right after a light drizzle. And this video was taken by a helicopter pilot while we were on ice. We were about less than probably half a kilometer away from them. And they were kind of videotaping these wolves roaming around while we're out there kind of melting our seismic nodes in. And you could hear them in the morning. It's an experience for sure. Also, as a part of this, we were doing a lot of active seismic work, and this was led by Kaya. So we were shooting normal incidents, as I said, into the passive arrays, and then also using her one component geophone string for the AVA surveys. We were using both kind of a polymer strike plate and a Betsy gun. Still working through the results. One thing that we might be coming to a conclusion is that we may need explosives to get really strong reflections, but kind of more to come with that later. And then just kind of as a summary, we're using these temperature sensors at different elevations to get the lapse rate. We've got this weather station, measuring ablation, these different environmental parameters, using these to inform a positive degree day model for melt production. And this will help us like contextualize our seismic data as we start to get a clearer idea of the behavior. And so kind of at this stage, my PhD student Zoe is kind of sitting on a mountain data and like working through it. And just I'll just take a second to kind of like show just a couple of the very preliminary results that we're starting to find, and kind of like look forward to like what we're interested in doing with this kind of over the next rest of the semester and over the next year. So specifically, like kind of looking at like the seismic tremor or the hydrologic connection and the seismic or the stick slip behavior, kind of contrasting between the two different arrays at the two different lobes. So yeah, one thing we've done is like looking at how seismic tremor, which is produced by kind of turbulent water flow through subglacial conduits, how this is basically related, how it relates to the observed surface velocities that we've kind of recovered from these continuous GNSS stations, as well as temperature, or basically a proxy for surface melt. So on the top, basically what you're seeing, the blue curve is the east array, and the orange curve is the west array, with the kind of the solid line representing the velocity from the GNSS stations. The blue, the other curve is the kind of the median tremor amplitude of that array through time. And what you see is, for both arrays, you have some tremor signal that's tracking the velocity to some degree that is exhibiting these diurnal swings. In general, the tremor that we find on the west side is lower than the east side, although there's some significant like peaks or spikes in the tremor on the west side, that kind of coincide with some of these peaks in velocity. Kind of similarly on the base, we see this like there's a kind of the melt or temperature, or what we're saying is proxy for surface melt, with tremor kind of lagging this by a few hours for the two arrays. And I'm not going to get too into what the lead lag time is for this, or what this implies about dynamics. I just got this plot a couple days ago, so we're very much in the point of like processing this data, starting to plot it up, look at the trends, and try to think about what this means in the context of the larger hydrologic system. So that was a tremor with time. Another thing we're looking at is like how this tremor varies in space. And so just like that as a first pass, you can just look at kind of this tremor amplitude at each node. This is just showing kind of a 3 hour window where the tremor band passed 1 to 10 Hertz, where just looking at the amplitude, and interpolating it between the nodes, you can kind of see these kind of contrasting regimes. So much less over this area at this time, much less turbulent water flow in the western array, where you have this kind of this density of trimmer kind of cutting down a line like kind of spanning the array that is roughly in the direction of basically parallel to the direction of glacier flow. So kind of some just like preliminary observations is that trimmer amplitude is higher and more persistent in the east array than the west throughout the deployment. The west array is showing more peak episodes, but their locations are kind of spatially inconsistent. So this kind of suggests to us that there's no persistent hydraulic tremor source, right? Or no um, or few persistent subglacial conduits that are kind of facilitating this like turbulent water flow that would kind of keep activating in the same way through time. And in the east array, it peaks cluster in this kind of southeast quarter and along a consistent line with a few hours outliers, which, at this stage aligns with what we think, if you had a kind of a large R channel kind of like spanning this array and on that side. Another thing that we're interested in is like how these different subglacial, hydrologic regimes are kind of impacting frictional slip, or like seismic versus aseismic slip. And so right now we're at the stage of kind of like looking through this data and identifying, what we believe to be kind of clear basal slip events. And at the stage, like Zoe is building a detection scheme, and she's identified quite a few what she believes to be, repeating events that are consistent with basal stick slip and asperity on the east side of the east array, where you have kind of no surface waves. You have a kind of P and S waves arriving at a time, with that's kind of time that's consistent with like, maybe 300-meter thick ice, which is about what we expect in that area. And so far we have found negligible or not, well, none actually at this point, similar styles of events, within the Western array. So kind of where we're at, this is kind of just a summary of this first pass of, these observations is tremor seems to be generally stronger and more sustained in the east array than the west. In the east, peak tremor amplitudes are aligning along an axis parallel to glacier flow, which we believe is consistent with the channel. In the west, tremor spikes can be large but are more intermittent and less spatially coherent. And this is kind of overall, we find this to be kind of consistent with more channelized drainage in the east, more distributed in the west, as Lynn hypothesized. And with the slip behavior, we're seeing basal frictional stick slip is apparent in the east array, but so far absent or negligible in the west array, which seems to, basically exhibit aseismic slip. So kind of the immediate next steps with this is we're refining the detection scheme and building a catalog of these icequake events in the east and west array. Ultimately, Zoe's going to use this to inform a machine learning detection scheme. And then we're going to better constrain the trimmer location using seismic processing approaches, such as this match field processing that Ugo Nani demonstrated worked really well for channelized systems on a hard bed. And then ultimately, we're going to be relating this like trimmer and basal SIXA to the environmental forcing, including the outflow, surface melt, precipitation, and then the larger scale ice dynamics that we're observing from GNSS and Lynn's observed from satellite observations. All this to say, this kind of sets up what we're going to do in year 2. So similar to last year, we're going to be deploying these 2 arrays of 88 smart solo nodes. Now we believe we have an idea of where a potential subglacial channel is cutting through one of these arrays, and that's going to inform a kind of some borehole experiment. So this next year, we're going to be drilling a couple, some holes in the bed in collaboration with Seth and Jacob at Maine and JERP. And the idea is that we're going to put down a plow meter that's being designed and built by John Lehman, as well as taking, these like optical measurements of what's at the interface and potentially trying to retrieve till, if there is till at the bed, but at some point between the two arrays, while getting measurements of subglacial water pressure that will inform, and subglacial water pressure and bed strength that will inform our seismic measurements. Another kind of new component to this year is that we're going to actually be doing a lot of ice penetrating radar. So we have Arlick Chang bringing an ice penetrating radar from Japan that's going to be out for the first portion. And then a professor at Washington University, Roger Michaelides, is going to bring out two systems with different frequency capabilities to basically start, get some good bed map or get some good bed mapping in on the western side, which is currently unmapped, as well as trying to fill in some of the gaps along the central and eastern side to better inform, our ideas of ice thickness and hydropotential modeling. And also kind of as a bonus experiment, since we have all these seismometers kind of arrayed out in this really cracked up crevasse field on the west side, we're going to be thinking about trying to do an experiment looking at thinking about fracture mechanics and tempered ice. So the three components that we're using for these observations is we're going to be doing basically instrumenting, a few cracks with a really dense part of the array where it's like, 20 to 30 meter spacing. We're going to be using repeat LiDAR drone surveys to kind of map the strain field around these crevasse tips, kind of at like maybe 2 to 3 day intervals. And then we have these custom extensiometers, which are devices developed by Luke at UW-Madison, which basically just measures, the string, a wire being pulled out or pulled back into a device. And so we can get really high resolution spatial and temporal measurements of kind of crack opening and closing at the tip. So this is something that's being spearheaded by my PhD student Zoe, and I'm pretty excited to see how it develops. So with that, I'll just say a huge thanks to everyone that's helped with this project. There's a lot of names on this screen. There's going to be, even more people this next year. And it's definitely not easy work. And, Southeast Alaska on the ice field, right? Like the first 2 weeks you're out there, it's just rain. You got thunderstorms. It's a real grab bag of, interesting conditions. But yeah, really rewarding and great to work in, and kind of thrilled and fortunate to be able to collaborate with everybody so far. So with that, I'll take any questions. Thanks a lot.
Questions for Dougal on the room or online? Dougal, I have one. Those smart solo units, can they do HVSR? You mentioned that.
Yeah, they can. We've used them successfully with HVSR before. We're running into some challenges, I think, just with like the glacier geometry with all the cracks and some of the assumptions that go into the HVSR to get like a successful acquisition. But they definitely can work for that.
Cool. Other questions online?
Well, I'll just pose the same question I asked of Luke. Other thoughts beyond his thought about sediment signals that can engage the ice field, JERP itself, and then kind of from a community perspective, do you have any other ideas right off the top of your head moving forward?
Yeah, I mean, I would really love if there was a possibility of being involved with the the new graduate student program, or, having students or flying students out to help participate in field work, if that was ever possible. I think that would be a really cool, means of collaborating.
Cool.
Other questions, comments?
Good.
Well, thanks, Dougal. Appreciate
Hey,
it.
thanks a lot.